Okay, take it away, Roman. Would you like an actual introduction?
Yeah, why not?
I'm very happy to introduce the godfather of MOPA. And
Godfather, please.
my beloved advisor, Roman, speaking on gaps, types, and pairs of models of arithmetic. And I forgot to mention his official title now of emeritus professor. So
That's right. Since August 26th. So thank you very much, Atar. And look, so I was reluctant to give talks here because I didn't really have much new to say. But then I realized that there was one paper, and I will give references later, that was published in 2012, that I never had a chance to talk at MOPAS or at the workshop. And partly because the work there is somewhat technical, it's highly specialized, it's really for the enthusiasts of models of arithmetic. But then, well, I realized that there is something to talk about, and maybe you will find it interesting, at least parts of it. And and it is well. Also, let me do the introduction when I do the introduction. So I will tell you what I will talk about, and while I talk about it, I will also extend the introduction a bit. Oh, now let's see. This is how does this work now? Okay, so this is now. Let's see. Okay, so look. So one can really formulate this question here. This would be about model theory of pairs, and then at some point, this became a fashionable topic in general model theory, and we know much about structure of models of arithmetic and their extensions. So we can ask this question: if you have a model of PA and its elementary extension, what can be said about this structure? Were in the language of arithmetic, together with a unary predicate for the submodel. How many non-isomorphic pairs like that are there in a given cardinality? What are the theories of those pairs, and so on? But it's really a premature question, as I wrote here, because if you think about it, most of results in model theory of arithmetic in the last half a century or more are about that. It's really about either extensions, elementary extensions, cuts, all kinds of things. They can be formulated in this language. So it's really a question that's a non-question. It's really much too general. So you want to narrow it to some cases that have a chance to become more interesting. So instead of just asking this in general, so you can ask, if you have a model and its elementary extension, what can be expressed about this extension in the first order way? And it already becomes a little bit more interesting. So because you might want to classify some theories of those pairs, and maybe something interesting comes out, and that also soon becomes complicated. But first, some background to it. That this question can naturally splits. That's what I call the Geifman split. Because of the Geifman splitting theorem, that you have those two cases. So the first case is to end extensions, and these are all kinds of results about elementary end extensions, and that's made possible thanks to McDowell-Specker theorem that says every model of PA has an elementary end extension, and there are various techniques and all kinds of things you can take and you can say about the kinds of extensions that you're getting. And then the second part of the split is the, sorry, how do I go back? Okay, it's not working well on my keyboard here, so I'll try to be more controlled. And the second case is the case of cofinal extensions. So, and that's because of Geifman's splitting theorem. And here, there is a dramatic difference between constructing elementary end extensions and just and just cofinal extensions. Because for cofinal extensions, you just use compactness, and to construct an extension of a given model K, and then by Geifman's splitting theorem, you automatically get a cofinal extension. And so different techniques apply, and there is almost a different theory of cofinal extensions. And actually, my original motivation for giving this talk was I was inspired by Lawrence's lecture in August about the cofinal extensions problem for fragments. And I realized that there is still much that we can say about the old-fashioned cofinal extension problem for PA. So originally this talk was supposed to be just about cofinal extensions, but as I was preparing this talk, I realized that much of it is very intertwined. The results about cofinal extensions also will refer to results about end extensions and vice versa. So now it's more general. And the split is not quite precise, and that is because I will not talk about it, but maybe part of the discussion of what are the possible isomorphic types of pairs, model K and its elementary extension. This could include all this work of Jim on lattices of elementary extensions, and then some recent work of Jim was that there is a special case of mixed extensions and with regard to the question of what kind of extensions can realize at the pentagon lattice. And then the mixed case turned out to be the sort of curious and still unresolved case. So maybe there's a third case of mixed extensions separate, but traditionally everything in models of PA splits into those two separate cases, end extensions and cofinal extensions. So we'll follow that split. And just a few words about, for those of you who don't remember, well, there is the Geifman classical theorem about cofinal extensions. Then if M is a model of PA and N is just a superstructure, an extension that happens to be cofinal, it's a model of PA minus. And if it's a delta zero elementary extension, that is an elementary extension. And this is a nice proof by induction on complexity of formulas. But then there is a stronger version of it. If both M and N are models of PA, and if the extension is cofinal, then it has to be, an elementary extension. And this follows from the first theorem of Geifman and Mathias Robinson, the Davies-Putnam theorem. And it's just like a small, because by this theorem, every sigma 1 and every delta 1 formula is equivalent to an E1 formula, just an existential, pure existential formula. And then this can be used to sort of show that any cofinal extension is actually delta 0 extension. But the use of this McDowell-Specker of the solution to Hilbert's sense problem here is essential. There is a very nice exercise. If you haven't done it, you should, in Richard Kay's book, that if you assume the theorem, the second theorem, then you can actually prove the MRDP theorem. So this is a model theoretic expression of the result itself. So there is something deep in it. But anyway, this is very special about models of PA. And I just wanted to say a couple of words, always, why all of this applies to PA and not some more general theories or fragments. So it's been known since Lassagne thesis from the 70s that those elementary cofinal extensions do not always exist. You can have models of I sigma n and not B sigma n plus 1 with no elementary cofinal extensions. They turn out to be too small. And the examples here are those pointwise definable models. When you take a model of PAs, for example, and inside you take the set of sigma n plus 1 definable elements, they will not have proper cofinal elementary extensions at all. And so Kay has looked at it, and then he proved that there is a dramatic difference between those two theories. One, induction without collection, and the other, collection without induction. It's dramatically different for collection and no induction. All, well, like I said, I should say that those are non-standard. Well, it is non-standard, which is a model of not I sigma n. So every model of B sigma n and not I sigma n has a proper cofinal elementary extension. And with regard to the first example, also Kay looked at it and he proved that, well, that those special cases where you don't have cofinal elementary extensions are really special. Models are too small, but with certain amount of saturation. And in his paper, there was this technical condition that later Jim named K tau, that certain models always have elementary cofinal extensions. And Jim looked at K's theorems and proved something very beautiful. And Wonky also did something about it in his thesis, that there is a version of saturation that Jim called tallness, just for general linearly ordered structures, and those admit proper cofinal extensions. So this is just to say that, if it's not PA, then this case of cofinal extensions becomes a little delicate, and this is all I have to say about it. We will not be doing anything general. Everything that will be done will be very specific to models of PA, and that will be also very clear from the techniques that will be used. There will be kind of a survey of various techniques that apply only to PA for various reasons, and you will see why. Okay, look, and do you hear me?
Yes.
Right, and so and try to ask questions now and then. Speakers always complained, and it's not that I really speak to my slides, and it's awkward. So so let's see what happens. I will try to go over some proofs later, and maybe we can have some more conversation when I get there. So let's see. So still in terms of the background, so what's specific about models of PA? Well, I will really concentrate on recursively saturated models. And so there are some classical results about it. And well, first of all, that this is the theorem of Zworyński-Stawi that says cofinal extensions preserve recursive saturations, and that the recursive saturation, that's very useful. And that's one of the fundamental results here. This is a result from the 1980s. And as a corollary, we have this that will be also of interest, that if you have a countable recursively saturated model and you have a cofinal extension that does not change the standard system, then you get something that's larger, but isomorphic to what you started with. So that also, so it can be used both ways. It can be used to prove existence of certain extensions with certain properties, but also goes backwards. If you have a model, then a countable recursively saturated model, it tells you something about what kind of elementary cofinal submodels it has, because by producing those extensions, you automatically produce cofinal submodels, and that's used over and over again. Okay, and so there is this thing. So this will be the main theme about certain properties of cofinal extensions and extensions in general. So there is this notion here of the greatest common segment. If you have a mixed extension, or if you have a cofinal extension, then you can ask what's the largest initial segment of the ground model to which no new elements are added. So that's the greatest common initial segment. And Zworyński proved several things about those greatest common initial segments. And one of them, that if you have a model of P and you have an initial segment that's closed under additional multiplication, countable model is closed under additional multiplication, then you construct a cofinal extension such that the greatest common initial segment of the model and its extension is exactly.
Okay, go ahead.
Okay, so what I was saying here, last remark, is that this greatest common initial segment, it's an interesting isomorphism invariant of the pair, model theoretic pair, because it's actually first order definable in the language of the pair. So we will come back to this. Okay, so the corollary, okay, I have to go back. So the corollary of this, do you see the bottom of the slide?
I can't.
Because for me, okay.
No.
Oh,
Yes.
can you see the bottom of the slide? So,
No,
so you look, you should be able to see it. It's the.
Nope.
Nope.
It was there for a second.
Right, because it's overshadowed by this. Let's see, maybe this will go away. Let's see. Okay.
Yeah, there you go.
I don't touch anything, it will stay. Look, so it says something now about first order theories of pairs. So you're in a countable recursively saturated model of PA, and you're looking at the set of all theories of those pairs, MK, where K is a cofinal submodel. And in addition, you can require that K is actually isomorphic to M. So you have this collection of elementary submodels, so they're all recursively saturated, they're isomorphic to M. And how many theories can you have? And already you have this enormous diversity, because by Zworyński's theorem, you can take any element, any cut I that's closed under addition and multiplication. And we know from other results that you can embed, for example, continue many models of PA with continue many different first order complete theories into any countable model of PA. So there are continue many cuts I like that, and they differ by their first order theories. and the cut is definable in the pair. So for different greatest common initial segments, you will get different theories of pairs. So you get this diversity of first order theories, and it's already a lot. So later on, so this is not, these are all ancient results. And this is just the beginning, because they will say, okay, so we have this one family, large family of models, and you have this large collection of theories, but the game would be to sort of narrow down the choices and sort of restrict, the case that you consider to various subclasses, and to see what can be said about those first order theories and isomorphism types. So this is what's coming up. Okay, so here the game is really, there are so many questions one could ask, and there is such a great diversity of those elementary submodels that maybe all of it is not really very interesting unless you really ask some interesting questions and you get some interesting answers. So you look at, this in general, this collection of elementary submodels of various types. So here I talk about cofinal case because that was the original thing that I wanted to talk about only. And you cite a recursively saturated model. And so Smorinsky results shows that you can get this great diversity because you can vary the eyes for the greatest common initial segment, and you get continue many theories. So what happens if you somehow prevent that? So what happens if all those greatest common initial segments have the same theory? Or what happens where they're actually isomorphic to I? Or what happens if you just fix I and the initial segment and still construct many cofinal extensions? What kind of diversity can you build in there? And it turns out that there are all kinds of things you can do, but not everything. And in particular, because we really want to sort of, again, restrict this to all kinds of cases where narrowing down gives some more interesting structure, that what happens if I is an elementary initial segment, not just any cut. In Smorinsky's result, this I can be any cut that's closed under addition multiplication. But you can say, well, let's take a look at elementary initial segments and let's see what kind of theory you can get there. So look, and now don't be scared or relieved. This is not the end of my talk. So this is usually what you show at the end of the talk, but this is very selected references because I want to make a point. So much of this is really this kind of research and many preliminary results, interesting results. This is work by Smorinsky, and I got to know all about it because those papers, as you can see, are from 1980, 1981. Smorinsky was visiting Warsaw in 1980 for a semester, and he was thinking and working with Kotlarski, and I was participating in some of those discussions, so I knew about those results, and this was all very interesting. But at some point, it was all kind of exhausted, and after 1981, essentially nothing more was added to all kind of open questions. Well, then there were some papers by Kotlarski, and I wrote a paper about something related, but there wasn't really that much interest and there was that much progress. And I don't think there's much interest now about it. But then I was on sabbatical and I was looking for some things to do. And I was thinking, oh, well, let me go back to some of those old questions. And I proved some preliminary results, and then I contacted him. Also, it so happened that Jim at the same time was working on very similar questions, but not in a countable recursively saturated model, but in a saturated model of PA. So then we wrote a paper together. Jim proved some beautiful results on top of what I was able to prove, and then Jim has his own paper, and there is much in it. And I don't think that many people looked at those papers. I think that there were two people who looked at our joint paper, and one person was Lawrence. I don't think Lawrence is here, and maybe he was joining us. And the other person was the referee for the paper who had some insightful comments, but I don't think it makes two people. Okay, so it must have been just one reader of the paper and nobody else much read the paper, but there is much in it. So recently I went back and I started reading and I said, oh, wow, this is really interesting stuff. Let me think about it. And so this talk, so this is all in introductory remarks, will be about what's in those two papers. So I will tell you not everything, but sort of an overview of what's in our joint paper. But also I will mention the results of Jim because they are related. Okay, so that's really, this is the end of the introduction now. Okay, so now part one. So things will be happening. So to make notation a little easier, everything will be happening in a fixed, countable, recursively saturated model of PA. So M is fixed until further notice. Okay, and so let me. So I will discuss this sort of various constructions and diversity among elementary submodels of M. Okay, so a useful notion is that of H. Chris Laskowski gave a talk recently, or maybe maybe last year, or at our logic colloquium on Fridays, and he was saying Ash. I'm not quite sure if this is well established. I will be saying H. Okay, so that's H of a subset or H of a structure is just a collection of complete types realized in A. Okay, so
the thing is, your use of age is a bit non-standard, right? I mean,
well, so what would you say?
Typically, the age is of a structure is a set of all finite substructures.
Right, but this is, you see, but here it's sort of an element sort of comes together because you have built-in column functions. It comes already with its column closure. So this is
it's roughly the same, yeah.
So then it becomes roughly the same. And I just like I like to be saying age of this, age of that. Sort of morally, it's similar enough, I think, in PA, not in general. All right. So the questions you can ask, so what is this diversity among various cofinal submodels? And here is this introductory things that inside M you have recursively saturated submodels of continuum many different ages. Okay, so you can construct, and this is sort of folklore, really, but it relies on this result by Simpson that's unpublished. And this is an exercise, but you have to think about this for a moment. About every Scott set, well, we're talking about countable Scott sets, but every Scott set has continuum many Scott subsets. It's not completely obvious. You have to think about it, how it's done, and this is the result of Simpson. But once you know that, then for every of those continuum many different Scott subsets, you can construct a recursively desaturated model that has this Scott set as the standard system. And then this is a routine, fourth embedding each of those recursively saturated models K X can be cofinally embedded into M. And each Kx has the standard system X. And essentially, the standard system tells you about the set of types realized in the model. So the sets of types are realized in each of those Kx difference for different x's. Yes, Ken, I see you.
Is that the Scott set of L omega 1 omega?
No, this is the set of, these are the models of WK0. This is the Scott sets of Scott.
Okay,
so these are the standard systems, the sets closed under Turing jump and weak Koenig's lemma.
Mm-hmm. Thanks.
What's the reason for calling it an age?
Oh, this is what Alf was complaining about. There is no reason other than this is a nice word and it's used for finite substructures in sort of modern model theory. They use this concept, an age of a structure, different type of finite substructures. But here, as I explained, here is sort of a single element or a finite set of elements. It's really the same as this column closure. The type is already there, so it roughly corresponds to the idea. And I like this. But this is very, very non-orthodox. No one has ever called it an age. Okay. And
Sorry, Roman.
by the way, so we choose results.
Roman, I have a question. Sorry.
Mm-hmm.
How do you build KX?
First, you just have this general result that says that if you have a Scott set that codes the theory of a model, complete theory or complete extension of PA, then there is a recursively saturated model that has of that theory that has this set as its standard system. So
Got
that's
it.
step one.
Okay.
Again, and then you do then you do an embedding of kx into m. But when you have this sort of back and forth procedure, in this case, it's really the fourth step only, because you do the embedding. You just make sure that the image, the range of the embedding is cofinal, and that's not difficult to do. You have much freedom in doing that. Okay.
If I understand, basically you're saying, sort of when you're building this recursively saturated model whose standard system is X, you are realizing a set of types that are realized in M, and you just make sure that you sort of build this sort of you do that cofinally high. You realize those types cofinally high.
But you don't have to do it all at once. So first you just do it this kx anyway. This is just this Scott construction. And once you have it, so this is a general thing. If you have a recursively desaturated model of the same elementary equivalent with a smaller standard system, then you can embed it into a recursively desaturated model, larger one. But an extra step needed it can be embedded in all kinds of embeddings, but it's not difficult to do it on a cofinal subset. It's a routine thing to do. Okay.
Okay.
So cofinal part is not really a problem. It's okay. So now, this is, as I said in the footnote, that whenever I will try to give credits wherever I can, but all those theorems and results that don't have credits that come from this joint paper with Jim. Okay, so the previous example gave there were lots and lots of submodels, and they differed by their age. So how about getting lots and lots of submodels that have all the same age, and the pairs are still not isomorphic? So I have some more formal description of the proof, but the proof is essentially on this drawing here. So I will try to explain the proof. Okay, so you start with a model M. This is your countable recursively desaturated model, and a countable linearly ordered set. So, and then you get a type, a minimal type, and I will talk more about minimal types soon. That's realized in M. And if you have this minimal type, you can use the minimal type and you get an end extension. This is all Geifmann's machinery. Once you have a minimal type, you extend this minimal type to the type over M, and then you make a canonical extension, this Mi. There's a canonical extension of M that's generated by a set of order indiscernibles of the order that have order type I. Okay, so what happens now then? Well, this model definitely will not be recursively desaturated, but what about the A? And now, because it is an end extension, and the argument now is that you are not adding a new type. So all the types of Mi are already realized in M. Now, how do we know that? And we know that because the minimal type is not only indiscernible, but it's strongly indiscernible. So the set of realization of the type is strongly indiscernible, so it's indiscernibility with low parameters. So the type is realized here by this set generating Mi, but also the type is already realized in M on a cofinal submodel. So now if you take a typical element of Mi, this is some Skolem term, some definable function on a sequence of indiscernibles and some parameters here, hardly visible, from B, parameters from M. So you go lower down to M, and above B, there will be a sequence of parameters ordered the same way as those parameters in the type, but now the type of the T of A bar B will be the same as T of A bar prime here in M, so it's already realized in M, it's an element of M. So we are not adding any new types to M. And now because of that, there are two things. Well, first of all, the age of Mi is the same as the age of M. Here I use the notation that I use before, types of MI are the same as types of M, but also because we didn't change the standard system, you can embed MI into M on a cofinal subset. So you get this family of cofinal submodels. Is that right? Well, okay, so I will skip this unless you have some questions. Yes.
So how about just getting K and K prime to be non-isomorphic without the M?
That's easier.
Well, doesn't that imply that? Is that stronger though?
Let me see. So let me just go back. It's hard for me to go back to previous slides. I don't know what happens here. Okay. So what you're saying that what? Just
No,
K.
I'm just asking if K, if you can just get K and K prime to be non-isomorphic,
Right.
not the pair.
That's what's happening here.
Oh,
That's exactly what's happening
oh,
here.
so but why do you say the pair then? It's not, they're non-isomorphic.
Because I'm interested in
Because that's the context you're talking.
right.
Okay. All right.
Right. So the evidence that the pairs are not isomorphic. Right. You're absolutely right. So you're absolutely right.
Okay.
The pair is not isomorphic because the K's are not isomorphic. So that's some abuse here. Okay, so I skip the proof, and so now there will be something that's will be a little longish and perhaps not that exciting. But then the thing will be to take a look at pairs M and K, not for cofinal extensions, but for elementary cuts. And there are some easier cuts to deal with, and there are more difficult cuts to deal with. And the first case is that what we call short elementary cuts. So a elementary cut is short. It is if it's a cofinal extension of a column closure of a single element. And an important isomorphism invariant of a shortcut is what we call a gap. So a gap, around each element of M, you have this gap of that element. And this is this largest convex segment interval of I, such that inside there are no initial elementary cuts inside. So the largest elementary cut is that does not contain A is just the supremum or infimum of the gap. And the largest elementary cut that contains the smallest elementary cut that contains A is the supremum of the gap. So you have A, you have the gap of A, and above it, you have K, which in this case is the elementary submodel, elementary cut of M. And then you have this elementary cut on the other side. So the model, every model is partitioned into gaps. You have countably many gaps. So we'll be talking about short elementary cuts, and we'll be looking at this is called the last gap of K. So what happens there? Well, so there are some simple things well, so this is what I already said, that those short cuts are really elementary. Okay, so this is and this is the last gap. This is the gap of A. And the property that is useful in dealing with them is that if you have, and this is what I had on my picture here, that every time you have this short elementary cut, there will be some element in the model that this is the sequence coded by C in M, such that it's an increasing sequence. You're going to make it an increasing sequence, such that K is the supremum of this increasing sequence. That's a useful property of these short cuts. And this is a simple proof, quick proof that there is indeed C like that. You just write this recursive type of X with the parameter A. K is a short model, and column closure of A is cofinal in K. And just say the nth term of the sequence coded by X is the maximum of the values of T of A when you say some condition that makes the sequence grow. So you just restrict the terms to those that have Gödel numbers less than n. Okay, and so you code the sequence, and the supremum of the sequence is K. That's useful. Okay, so another useful property of those shortcuts is that if that not just short, but you just have any elementary cut that has this property, what we call omega coded cuts that have inside, and there are supremum of a coded omega sequence, then you define omega in the pair. And 0 means as the definition without parameters. Okay, and how does it work? Well, a simple definition with parameters is that n is in omega if in mk the nth term of the sequence is in k. But that's a definition with parameters. And now it's a simple observation that it's good to know that every time you define in a situation like this, when you have a formula which defines an omega with some parameter, then there will be a parameter-free formula that also defines omega, because you use the same formula and you just vary the parameters, and you say that whatever parameter you take, your formula defines a set that's closed under successor, then your element is in that set. And okay. And so since there is one parameter, then now I worry about something here. Do you worry about something here? I think it should.
I
Well,
think it's
you
okay.
say, yeah, you're saying that X must belong to all those. Right, it just says, right, it's fine, it is fine. You just say, well, that X must belong to all those sets. So in particular, it belongs to the one that's defined by this particular C, so it must be in omega. And it cannot be anything less than omega because it's closed under successor. Okay, so that you get your definition of omega. And once you defined omega, you can define all kind of other things. So once you have omega that's 0 definable in the pair, then you can also define satisfaction for K inside MK. Okay, and how do we do this? Well, this is by writing a formula which says this, that X thinks of X being an N, and you think about formulas of quantifier complexity N, and the formula will describe S as a set satisfying Tarski's conditions for all formulas of quantifier complexity X. And K stands for K. K stands for the cut. And then once you do that, then something will be true in K every time, whenever in the pair there is some code D, and you want the D to code something, to code this satisfaction relation. This is D codes sigma X truth for K in M. And then you say that the pair phi A is in D. So this theta decides that phi of A is really true, and this will happen if and only if phi of A is really true. So that's the definition. That's the 0. That's the parameter-free definition of satisfaction. So now we have omega defined in MK. We have satisfaction for K. So then, starting with that, you can define all kinds of other things. It gives you a tremendous handle of how much you can say about this whole model theoretic pair MK.
Can I ask a quick question? I don't know if this is known, but if you can you go backwards from if you know that omega is 0 definable in the pair? Does that tell you something about the structure of K inside of M?
Nope. And this will be on my coming up slides.
Okay.
The answer is not always. That in this particular case, yes, and in some cases that actually I will discuss, the answer will be no. Okay, so Zorinsky already noticed that, and it was based on some results of Henryk Kotlarski, and but Jim also used this argument in his paper that was, so I just wanted to give you a sort of outline of Jim's argument. So the argument will show that using the fact that satisfaction for K is defined in MK, you will have infinitely many theories of pairs like that. And how do you make it? Well, we have to make many different Ks, and they will be different. The difference is about, made by what is being realized in the last gap, what's in the top tier of K inside M. And so this goes back to Geifman and constructions of what's called independent minimal types. And minimal types can be constructed in such a way that you construct a recursive base for a type. This is a recursive construction, and that later, and about which you show that you have this recursive set of formulas that has a unique extension to a complete type, and that type turns out to be a minimal type of Peano. But this is done instead of constructing just one type, you will construct a whole tree, a binary tree of those types. So what's involved is one recursive sequence of phi i's and a recursive sequence of theta i's in such a way that, so the sequence of phi I will make sure that the type you're constructing is minimal. And those theta i's will make sure that what you're getting continuum many different types for any set of natural numbers. The type where you include theta i's for I in I, and you exclude theta i's for the complement, is a consistent type. And this part will make, and is done in such a way that makes the types independent. So this is all in Jim's paper. It's a nice, elegant construction. It's very sort of somewhere implicit in what Geifman was doing. And so we have this family, a large family of continuum many types, and they're all minimal types. Some of them will be realized in M, some of them will not. But the construction is such that if I is in the standard system, then pi will be realized in M, because this will be a type that's coded in the standard system. So there is standard system saturation. So for all the i's in the standard system, these minimal types will be realized, and they are all independent. But independent means, one way of defining independent types is that they cannot be realized in the same gap. Well, actually, this is a property of independent types. They cannot be realized it can be proved. So if they are realized, they have to be realized in different gaps. So now if you have those Ki is a supremum, is a short model that's a cofinal extension of something generated by AI, this last gap of Ki cannot contain an element that realizes Pj for a different j, because the types are independent. And because of that, well, the pairs will be non-isomorphic, but also they are not elementarily equivalent, because you have satisfaction and you have omega, and using satisfaction for Ki and using omega, you can say, and also using the sequences here, you can say that in this structure, the last gap realizes Pi, and in this structure, the last gap does not realize Pi. So you get elementary and equivalent pairs and continuum, countably many, because you will get them only for the i's and j's in the standard system. It's a very useful construction. Do you have any questions? Okay, so I'm not hearing questions. Let me move on. Okay, so now there is more about this construction. So there is something about different types of types, and P of X is rare. In every model, each gap has at least oh, this is terrible what I said here. This should be most. Well, just the most. So you see, in other words, yeah. Ken? Oh, I don't hear you. Okay, look, so this is terrible. But anyway, so rare types, well, they're called rare because they are rare. If you're in a gap, well, if there is one element realizing the type, there will be only one. You cannot have two. And because of that, we call those gaps that realize the rare type labeled, and you think about this type of this unique element there as kind of a label for the gap. So an example of rare types are minimal types. Well, this requires a proof, but so in the construction that Jim gave, the rare types are used. So you can formulate this as a, okay, so before I formulate the result, so the opposite of a rare type are a ubiquitous type. And so so this is something that is both a proposition and a definition at the same time. So if a gap is not labeled, then it turns out, and this is a simple proof, that's an exercise, to show that the type of each element realized in the gap is called ubiquitous. And ubiquitous means that the types is realized arbitrarily high and arbitrarily low in the model. It's just realized all over the gap. And so you have this dichotomy that either a gap is rare and it cannot have any ubiquitous types, or the type of every element is ubiquitous. So this is this dichotomy of different. So this gives you also an example of short cuts, which cannot be short elementary cuts that cannot be isomorphic. There are those that realize rare types because they realize, for example, those minimal types. And it has to be proved that there are ubiquitous types, and this can be proved, but it requires some work. So there are, so this is the simple proposition about them, that if you have those short cuts, one is supremum of one of the gap gamma, and the other supremum of gamma prime. So these structures are isomorphic. There is an it's an automorphism of M that carries this cut onto this cut, if and only if the ages are the same, the gaps realize the same type. But it also means, because it all happens in the recursively saturated models, they are homogeneous. So if the ages are not joined. So now, and these are all simple exercises. These are all simple things to verify. And from this Jim's construction of those infinitely many non-elementary equivalent shortcuts, well, you can formulate like this. There's an infinite set of labeled gaps, all those labeled by those minimal types realized in them. And the older ages are different. Okay, so this is part of the partition of the model, and in those gaps you have all kind of types, and those gaps have nothing in common. The ages are different. So there is one thing that's left. So in the paper there is this a little embarrassing thing. So this is a quotation that by a bit more elaborate construction we have been able to prove the following counterpart. Theorem A is this corollary that I just mentioned. So this is the same result, that there are infinitely many different theories of pair K at the same situation, but the last gap realizes a ubiquitous type. But the proof is not included in the paper, and there are two reasons for it. This was Jim's argument that was rather complicated, and I thought maybe it's not really for me proper to have this very complicated result in this joint paper, but also I didn't completely understand the proof. So I was trying. So in a sense, this is something that if anyone feels inspired by this presentation here, you might want to try to prove it. And maybe there is something more than there. But anyway, so this is, I'm not quite sure if this is, if we have been able to prove. Jim has been able to prove it, but there is no, notes are preserved somewhere, but this is somewhat of an open question. No, this is Jim's result, but it's not published. It's an unpublished, I can say this is an unpublished result of Jim. But this just adds to this kind of complexity of what's happening here, because we're just at the tip of an iceberg. Those shortcuts is just the beginning of the story. So let me tell you, I see that it's already 7:50. I don't want to go over time, but let me tell you what follows, what is the rest of the story. So once we have shortcuts, so shortcuts are the suprema of the last gaps. So there is a short case and there is a co-short case. And the co-short case is on the other side. If you have a gap, so you look at the other end. The upper end of the gap is a shortcut, and the lower end is the co-short, and it's also elementary. One can prove that it's an elementary cut. But it cannot be short and a cut cannot be at the same time short and co-short. And again, it's easy to prove. But still, there is some doubt cofinality. So this is this combinatorial concept of cofinality, not a set theoretic cofinality, but arithmetic cofinality. Arithmetic cofinality of a cut or initial segment. So this is the supremum of all those elements, such that if you have any coded sequence of length A, whose terms are in the cut, then they are bounded. There's a bound for that sequence. So you look at the supremum, the largest A. There won't be a largest A, but you look at the supremum of all those A's. So for example, cofinality of any cut will be always greater than omega. Okay, omega is clearly smaller than the cofinality defined this way. And this is a combinatorial property defined by Laurie in his thesis. And one of the things for us is that this is this other thing that's an isomorphism invariant of a pair, and it's zero definable. I just wrote it. This is the definition. It can be translated into a fourth order definition. So now what about those co-short cuts? Well, so this is the definition. So those are the infima of gaps. And there is something, look, so Jim just proved, well, I just talked about Jim's proof that you have infinitely many theories of pairs with the shortcut. But Henrik and I, in this paper from something like 1997, we proved that it is not the case for co-shortcuts, although they look very similar. So when you look to the other end, they all realize the same theory. The least gap above K can contain all kinds of elements, everything, all those different gaps that contain different elements. This is sort of about, Atara, this is about your question now. This is this case where you have cofinality of K omega. Omega is definable without parameters in the pair. Structures are can be non-isomorphic because whether they are isomorphic or not, it depends on what's realized in the gap that determines the cut, the first gap above the cut. But still, there are lots and lots of non-isomorphic pairs, but they all share the same theory. And actually, this is sort of contradicts claims that Zworyński gave in his old papers. He was claiming that the converse of this is true, but he didn't give any proofs, and rightly so, because actually this fails. This is you have just one theory of those cuts. So even though okay, so as a corollary, right? So even you in the cut. In the pair, you can define omega through cofinality. Satisfaction cannot be defined. If you could define satisfaction for K, that would be fine, or satisfaction for the gap, but the gap is not definable over K and everything's failed. So another corollary, this is just I already said, that it gives us examples of structures of pairs that are elementary equivalent but not isomorphic. That's interesting on its own. And by the way, so how does one prove things like that? Well, the same way as one always proves elementary equivalence of structures. This is by playing Ehrenfeucht-Fresser games. So this is not something very straightforward. You have to play this game, and it's a subtle game, but something that I wanted to prove from my early days after my college days, and I always failed because the things were sort of not quite right. But eventually we figured it out, and it works. And this will have some influence on what I will be talking about next week in a saturated case. But one of the interesting open questions is that if you can get an example like this among the shortcuts. Okay, so could be so by this result, this is from our paper there, that we have infinitely many non-elementary equivalent pairs, so they do exist. But if they are elementary equivalent, do they necessarily, can they be non-isomorphic, or are they necessarily, for the examples in Jim's case, this is actually true, because to be elementary equivalent, they have to realize the same minimal type in the last gap, so they will be isomorphic. But what about, for example, examples where the last gap of K is equal to type or other situations. And this, it's somewhat known problem. I talked about it to Jim and to other people. This is something Erez was thinking about when he was working on his PhD thesis, couldn't really decide how to do it. I think this is an interesting question for people who are interested in types and recursively desaturated models. Look, so let me just tell you. Let me just tell you what's happening later. Let's see. Right. So this is not. Maybe I'll just take 2 or 3 minutes just to finish part 1. Okay, because then Zworyński also did all kind of other things, and another interesting tool is that ascending sequences of gaps. So what happens there is that if you have an initial segment of a model M that's closed under successor, and then we say that C codes an ascending I sequence of gaps, if I codes a sequence such that each next element in the sequence is above the scope closure of the previous one. So you can think of them as really very fast growing. They're as fast growing sequences as you possibly can, coded sequences. And then this is an exercise, so for each such, and they do exist in a recursively desaturated models, you have those ascending sequences of gaps of arbitrary length. You have sequences of length, the whole model. Well, not coded, but each initial segment then would be coded. And if you take a supremum of such a sequence, then you get an elementary submodel, and they are so-called tall elementary submodels. They are not short, and because they are recursively desaturated and they share the same standard system as M, they are actually isomorphic. So you get all kinds of isomorphic copies, and from that you, for example, you get diversity, but also you can get this, what we're also interested in, what kind of constructions are not giving you anything new. And that's important for this whole theory of recursively, of submodels in a recursively desaturated model, that you take any 2 ascending sequence of skies of length omega, then the models you're getting are just isomorphic. You're not getting any diversity from that. Now, Zworyński was claiming that it's also true for longer sequences, which later turn out to be not true, but maybe I will talk about it next time. But I think this is just enough for one evening. So what's happening next week is that I will move to part 2, and this will be essentially a survey of what Jim did in his paper on saturated models, which touches upon very similar themes, but now not in the recursively desaturated model, but in the saturated model, where things work smoother because they are saturated. And there are interesting results, and there are some interesting open problems there as well. And then I will move to some other themes from our joint paper. There is still much to talk about, which we're very far from. We're not yet at the level where things get complicated. I don't want to discourage anyone, but the complicated things will be happening later. So maybe this is 8 o'clock, so maybe it's a good time to stop.
Okay, so we can do our clapping, I guess, and take questions if anyone wants to go ahead and unmute themselves.
Roman, can I ask a potentially sort of completely unrelated, but and also potentially bonkers question?
No.
Okay. So is there any sort of situation known where you have an elementary pair of models of PA, which in any sense are quote unquote tame?
Well, you see, you include PA, so you would have to be a very special, you would have to sort of define tameness in a very special way. So perhaps the closest you come in would be in generic cuts that I would talk, so that a cut that doesn't add any complexity to something that was complex to begin with. And those would be generic cuts. And I will talk about them next week.
I guess what I'm asking is, this is probably totally off the wall, but for example, some kind of relative quantifier elimination, right?
Right. No, that's what I mean. And generic cuts. This is not my work. This is something that Kay and Lawrence.
That was some kind of relative quantifier simplification.
Right. So they will look. So they have this notion, and I will not talk about it in detail because they have this rather complicated concept of what a generic elementary cut should be, and they do have some sort of quantifier elimination. That was their aim, but it didn't go all the way through. You eliminate quantifiers up to certain level and certain shape of
That's not surprising, but
and then you get something that's interesting, but it's not really earth-shattering.
okay, so is this is generic? Is it called generic cuts or?
Yeah, there is a series of
Okay,
papers,
okay.
and I
I'll
will,
go with that.
I will mention something a little bit about them next time. But it's really something very technical and something very specific to the requirement what makes a cut generic, and it's not this work in a sense is not quite finished, although the results are interesting.
Sort of a general broad theme and sort of general model theory, right? Trying to find tame elementary pairs, right?
Yeah, but I think though in arithmetic it would be quite revolutionary to call anything tame.
Well, that's the thing. I mean, it's be interesting.
Yeah, I was asking for something that I called gentle expansions, but essentially no. But this is sort of like Attar's work, on neutral expansions, and things like that. So we try to, but and
it's a relative thing, right? It's always tame relative to the base theory, right? So you basically flatten out arithmetic to consider that tame. It's even getting worse.
Right. No, but this theme comes up in various disguises, but there is nothing ultimate that one can say. I don't know if Jim has something to, or Laurie something to add to it, but.
Looks like Ken has a question.
I don't see Ken.
You're still muted.
Okay. I saw that many papers were in the Notre Dame Journal of Formal Logic,
yes,
which has an illustrious history in dealing with logic and with, I think, models of arithmetic itself anyway. In fact, I think it went back to the 40s. There was an important paper by Skolem that appeared in the Notre Dame Journal. Do you guys know the title of the paper?
Well, I wasn't aware of it.
Oh, okay. I will look it up and bring it next time.
Excellent. Well, we can do some search in between. I'm sure it's searchable, but will be interesting.
Yeah, no, I remember looking at it. It was an important paper in this time.
Well, that's because his original papers were like from 10 years earlier or even more.
Yeah, the 30s. Yeah.
That would be interesting.
Roman, I had a quick question. I'm not sure if I had I have a small grasp of, so I might understand the answer, but was there, between co-short and short, did one imply the other?
No, the one contradicts the other. They are mutually exclusive, but they are, in a certain sense, negligible sort of sets of cuts because there are only countably many of them. And the model, even though it's countable, it has continuum many cuts, and there's a great variety. So this is really a very special case that we discuss at the beginning, and then we will discuss some other cases later. But short and co-short are exclusive; they cannot. They are different.
They're kind of like dual notions. You take an element and you look at its gap, and then it determines the set of all things that are less than some Skolem term of that A, so less than T of A for that.
No, it's not that Attar.
I'm saying that's the supremum, right? And that'll be a short model.
Right.
And then co-short will be the infimum.
No, the co-short will not be the infimum.
No, it's not?
No, because those will be what we call interstices later. Now, because this is up, you can only go that far. But down, you can go down as much as you want. You can the gap is the supremum of those things that do not touch anything in the gap. So you cannot, this co-short thing is much different. Right. So in other words, the gaps are, what a co-short case is somewhat more mysterious.
is the fact that co-short and short are exclusive, is that basically because same thing for cofinality, is upward cofinality
Yes. Yes,
equals omega and downward cofinality equals omega are exclusive?
right. But also it's not difficult to show that co-short models are tall. They cannot have the largest gap. Gaps are dense. Between any two gaps, there is another gap. So the cut below, the one that's co-short, the one that's infimum of the gap, cannot have the last gap. And that's simple recursive saturation. Yeah, no, because cofinality will not do it, because you can both have cofinality omega. So the downward cofinality omega and arithmetic cofinality is the same, because if you if you have a co-short cut, then there is the decreasing omega sequence whose infimum is the cut. And there is no such sequence going up, but still the cofinality of the as defined by you is still omega.
Well, I thought it was because we have the recursive saturation.
Right. Well, let's see. In a non-recursively saturated case, well, then of course you can be short and not short and co-short. But then you will not have those sequences that they require recursive saturation. Right. So those short and co-short, they really make sense in a recursively saturated case. In general, all kinds of things can happen. Gaps, you define those gaps, you can have gaps of any order type, linear type. This is like, you have models generated by elements realizing a minimal type. You can order the gaps. Essentially, the order of the model is determined by the order of the gaps. They can be well ordered. There can be all kinds of things.
Any other questions?
All right, look, so before we finish, I just want to tell you that my point in those, there will be some results maybe that I will talk about. I think I find them interesting, and there's some interesting constructions that Jim came up with. But in general, what I'm going to do is really some kind of an overview of various techniques. Some combinatorial properties will come up, regularity, irregularity, strength, what kind of things will be used just to prove certain things about what's happening in what models. So you might find it interesting. For those of you who haven't seen it before, you will see it. And if you have seen them before, it probably was a long time ago. So you may enjoy seeing them again.
So it has probably been a long time since I've seen it.
Well, it's been 10 years.
I'll look forward to it.
All right. And there will be open questions. Well, there are some open questions already. Okay. Thank you.
Thanks again, Ron.
Thank you.